Oh yeah, so we'll talk about confinement and supersymmetric gambling theory and the Lattice.
Thank you. Thanks to the organizers for this nice workshop. Actually, Andreas has invited me here to present some summary of the lattice results of supersymmetric Yang-Mills theory and also theories with adjoint fermions on the lattice, which is a rather broad topic. So what I decided is to make rather an overview and review some of the results that we obtained here. And we can then later on, if you want to know some more of the details of the results, ask some further questions. So actually the talk will be 3 parts. The first part, I will just talk a little bit about continuum, supersymmetric Yang-Mills theory, and also the relations to other theories with adjoint fermions. And then I will talk about or review and summarize the lattice results of supersymmetric Yang-Mills theory. And in the end, I will talk a little bit about an ongoing project of investigating the semi-classical confinement of supersymmetric Yang-Mills theory or Yang-Mills theory in general. But let me first start with introducing theory. So the supersymmetric Yang-Mills theory has mainly been considered as part of beyond standard model supersymmetric theories. But later on, it was also a toy model for understanding better the confinement mechanisms. There are analytic calculations of condensates and beta functions, etc. And then there's also this orientifold planar equivalence, which relates this to QCD. So there has been a lot of development in the theoretical understanding of this. And then later on, there was also by Mithat Ünsal and other people in more deeper investigations also of the semi-classical calculations of the compactified supersymmetric Yang-Mills theory, and also in general in these considerations also the semi-classical analysis of the theory plays a major role. The Lagrangian looks similar to QCD. The main difference is that we have now just one flavor of Majorana fermions in the adjoint representation, which makes it in some respects similar to pure Yang-Mills, but in others more similar to QCD.
Motion on Majorana, for example, it's not simply continuous to integer. So if you are going to go with Euclidean lattice, then they will say that it will be a problem. Right?
Yes, there's a principal problem about this, but there are first of all theoretical arguments how to deal with that. And I can talk about this later because this is goes in some of the details of the whole derivation. Basically, you can try to the fermions are usually integrated out, and then you can somehow just look at, for example, the spectrum of the theory, and then you can take what, for example, half of the eigenvalues, and this corresponds then to something that you can connect to Majorana nature. But this is already something putting the theory on the lattice, some complication. The important properties of low energy or low temperature supersymmetric Yang-Mills theory is that it is expected to have a QCD-like running of the gauge coupling from to be a confining theory, and then also you expect that you have gluino condensation and chirosymmetry breaking. Since supersymmetries should be preserved even at low energies, there should not be any kind of spontaneous or anomalous supersymmetry breaking. therefore, there must be some multiplets of bound states that describe the low energy effective theory. And the simplest possible way to arrange these kind of bound states is a chiral multiplet. So this means we need a scalar, a pseudoscalar, and a fermionic particle that all have the same mass to describe the lowest bound states of the theory. In the literature, there exist basically two suggestions for these kind of states, which are either gluino balls, which means meson-like states, and then you have also the possibility that these are just glue ball states. And then you have a combination of the fermion and the gluonic particle, which is possible in the adjoint representation, which makes up the fermionic content. So this should be the low energy effective degrees of freedom. So yeah. We don't. So actually I've written it here already, there is an expected mixture between these two. And there's even the difficulty that on the lattice, this mixture can be different from what you expect in the continuum. So it's really difficult to tell one of these from the other part. But in the literature, there are some discussions whether the lowest multiplet is rather of one or the other type. So it's, but I don't know. Yeah. So it's you have only quantum numbers to tell states apart. So therefore, it's difficult to you cannot really distinguish them in a gauge invariant way. So one remark I want you to add is that if you increase the numbers of flavors in and going away from supersymmetric Yang-Mills theory, you have to be careful because as everyone knows, is that for a large number of flavor, you lose in a general QCD like theory, you use asymptotic freedom. And then there's even a lower range, which is called the conformal window, where you expect that the running of the gauge coupling changes and it develops a conformal fixed point in the infrared where the running stops. And the important point here is that for the adjoint fermions, this number is much lower than for the fundamental representation. So if you compare supersymmetric Yang-Mills theory results, then for example, with lattice results in which have a larger fermion content, it can be that you are in a completely different regime. If you just look at perturbative estimates, I think the asymptotic freedom is at around 11/4 is the estimate where it is lost. And for the lower end of the conformal window, of course, you don't have any perturbative perturbation theory is not reliable, but the estimates are that this is either just above 1 or just above 2, depending on what kind of methods you are using. What lattice results indicate is that actually the theory with 2 Dirac fermions is already in the conformal window. And the reason why this theory has been so heavily investigated, so I listed here only a subset of all the lattice results that are available for this theory, is that because it has been suggested as a minimal walking technicolor extension of the standard model, and therefore it has been heavily investigated. What we also did, so Andreas Biaggiolini and others, is to investigate the theory with one adjoint Dirac flavor. And this turns out to be very difficult, and it's still not clarified whether this is whether this still shows a conformal behavior. You have to remember that on the lattice, if you are studying this kind of slowly running, you are limited by the scales. So you have only a window between the scale given by the lattice spacing and the lattice volume. So it's rather limited that what you can do, but we are still studying this, and there will be shortly also an update on the results concerning this one flavor theory. What I can say is that actually a large number of lattice results for all these kind of related theories exist. So we have lattice results for, I called it here half a Dirac flavor. So this is supersymmetric in this theory. Then for the one flavor, as I mentioned, then also for 3 halves, which are 3 Majorana flavors, and a large number of results for 2 flavor. But even for theories with a mixture of adjoint and fundamental flavors, there are already some. Yeah, I mean, this is the ultimate goal. So to extend the results for the beta function on the lattice so much that you can match to the perturbative results in the UV.
Then you know what the number of flavors on that side.
Yes, but this is only valid if you go at the upper end of the conformal window, where you lose asymptotic freedom. The lower one is so the lower one is controversial because this is really in the non-perturbative regime. Yeah. The lower window of the function than C. In principle, yes, but so all kind of approximations indicate that for the adjoint representation, there's only a very small NC dependence. For the fundamental, it's of course different. I wouldn't expect it to be as dramatic, but not immediately separately up. Yeah. What number of flavors is reliable? But there's no control. Now, that's a bit fast. Take the largest value, which is not necessarily yeah. So depends on how reliably it's not. Well, it's not parametric. Yeah. I mean, I think it's okay. I believe that is false. Yeah. No, I mean it's a very difficult calculation, and also various other methods besides lattice simulations have been tried. For example, Schwinger-Dyson or FRG studies to fix this, and therefore you have also different estimates. But yeah, I mean, no one knows how reliable they are. No, unimaginable. Yeah. For such small flavor. Yeah, it's 4 Majoranas. So you so I think yeah, again, doesn't sound like that. So yeah, it's actually, if you increase here the number of flavors, it's only very tiny. So I mean, between if you just take the perturbative estimates, it's something just above 2, and then the upper limit is 11/4. So yeah. So it's a very tiny range of flavors. So the other thing I also want to mention is what happens to the confinement-deconfinement transition in supersymmetric Gamma theory. And of course, like in in Young-List theory, you expect a certain deconfinement transition. And the good thing is that if you add the adjoint flavors, they don't break center symmetry. So you have a deconfinement transition that is valid for any kind of fermion masses that you can determine reliably. The additional thing is if you go to the massless limit, then as like in massless QCD, you also have spontaneous chiral symmetry breaking. So you have in principle two different transitions, which is a chiral transition and a deconfinement transition. And there have been estimates by, so there are calculations and considerations of Toft anomaly matchings, and these give a bound for these kind of transitions, namely that the chiral transition should be above the deconfinement transition. Usually in some papers for supersymmetric Young-List theory, it is considered to be the same, but there is no necessary proof of this. Now, if you consider fermions with antiperiodic boundary conditions, so the normal thermal partition sum, but if you now switch to periodic fermion boundary conditions, then you are investigating a twisted partition function, which is in fact nothing but the famous Witten index for supersymmetric theories, or more generally, you can call it a twisted partition function. And what it counts, because of this additional -1 times this fermion number operator, is the difference between bosonic and fermionic energy levels. And since all states except the ground state in this supersymmetric theories cancel between bosonic and fermionic states, it just counts the difference between bosonic and fermionic ground states. And since for supersymmetric Young-List theory, this is a fixed number, just a number of colors, that correspond, this twisted partition function is independent of the radius r here. Now you 1 over temperature has to be replaced here by this kind of radius, because it's rather a compactified theory than a finite temperature theory. And therefore, in this compactified theory, no phase transition is expected as long as you have this periodic fermion boundary conditions. This has been studied in quite some detail. So even for larger number of adjoint fermions, and you can show that in all cases, if you just look at the perturbative effective potential for the Polyakov line, phases, then you find that the perturbative contributions from the gluonic fields are counteracted by the adjoint fermions. And therefore, if you consider a larger number of flavors than in supersymmetric Young-List theory, you immediately will see that you end up in a confined phase if you consider periodic fermion boundary conditions. More precisely, one has to be careful how this confinement really appears here. Usually at strong coupling, the confinement is that the Polyakov loop averages to 0, appears because of large fluctuations of this Polyakov loop, which are, so to say, just given by the harm measure of the theory. Whereas in the perturbative regime with a larger number of fermions, you get fluctuations around the configuration of the Polyakov loop eigenvalues, which just puts you to a 0 Polyakov loop. And therefore, usually these kind of two different reasons for this confined regime are called non-abelian and abelian confinement in some works. What is important is that the specific case of supersymmetric Young-List theory is quite distinct from the ones with a larger number of fermions, because there you have an exact cancellation between the perturbative contributions of the fermions, of the adjoint fermions and the gluons. So basically this means that from this perturbative perspective, the theory remains closer to a strongly coupled regime. Yeah, even at this small compactification radius. This has also been a motivation to study these theories in a semi-classical regime, because you can apply this semi-classical method at a small compactification radius. And it was conjectured that molecules of fractional topological charged object should be responsible for a confinement in this kind of regime. So these were just results from the continuum investigations of supersymmetric Young-List theory. Now we want to study this on the lattice to get some further insights. And we also want to see whether we can match these theoretical predictions and first of all confirm in that way that we can reliably simulate the theory, and then also look at, for example, how reliable this semi-classical description of the confinement is, and whether one can extend these kind of conjectures about the confinement in supersymmetric Young-List theory. The problem here is that if you formulate the theory on the lattice, any kind of local lattice formulation breaks supersymmetry. This is unavoidable for any kind of theory that you break supersymmetry on the lattice. So it can only be recovered in the continuum. And in addition, there are some additional practical and technical challenges. We had we already mentioned here the Pfaffian and the Majorana nature of the fields, but I won't go into details here concerning these kind of more technical problems. Yes, but then, yeah. This works only for maximally supersymmetric theories. So for n equals 4, you can go to this twisted formulation, and then you can preserve, because you need to have some kind of scalar fermion. I'm not aware of this. I only know the construction for n equals 4. So for 2 dimension it works, but yeah, of course. But for 4 dimensions there is. Yeah, maybe we can discuss it afterward. The thing I just want to mention here is that if you formulate the theory on the lattice, you have to be careful with 2 different kind of symmetries. First of all, supersymmetry. I already introduced a Gluino mass term, which leads to a soft supersymmetry breaking. And then you have also a chiral symmetry, which is in case of supersymmetric Young-List theory, first of all, broken by the anomaly, but in contrast to bond-flavor QCD, you have a subset of a discrete subset of symmetry, which survives this anomalous breaking, and then you have spontaneous breaking due to the presence of this Gluino condensate, which makes basically the chiral symmetry breaking in supersymmetric Young-List theory. Now you formulate the theory on the lattice, and this does spoil all of these 2 symmetries. So you break chiral symmetry and you break supersymmetry if you use the most efficient formulation, which are just Wilson fermions in this case. So you have to recover supersymmetry in the continuum limit, and in this quantum field theory, you have, of course, to do some fine tuning. So you have to add counterterms to the action, and then tune the signals, tune the coefficients according to signals for the restored symmetry. in supersymmetric in n=1 supersymmetric Young-Mills theory, this fortunately turns out to be very easy. So first of all, chiral symmetry is actually similar to also what you would do for simulations with Wilson fermions and QCD. So you would have to tune the mass towards some critical value where you recover the symmetry. The good thing is that you can analyze now the supersymmetric Ward identities and all kind of operator mixings, and you will find that in that case, the same tuning of the same parameter is also enough to recover supersymmetry in the continuum limit. So you end up with basically doing the same thing that you would also have to do for QCD. With one additional difficulty, which is to define a chirosymmetric point, because we don't have the same chirosymmetry as in QCD. But what we have seen is that you can use a kind of signal which corresponds to an adjoint pion mass. It's a counterpart to what would be the pion in QCD, and tunes the signal according to this. But we later checked also that this is consistent with supersymmetric Ward identities. Actually, the fact that chirosymmetry is enough to recover supersymmetry in this series also means that if you have some formulation with chirosymmetry on the lattice, like what's called Ginzburg-Wilson fermions, then you don't need any kind of fine tuning. But these kind of fermions turn out to be very expensive to simulate. Therefore, they are usually not enough to extract some information, especially for the bound state spectrum of the theory. So the first results I want to present here are the bound states of supersymmetric Young-Mills theory. And what you can see here is basically a scalar particle, then a pseudoscalar particle and this fermionic particle. And as I told in the beginning, we expect that they should all have the same mass. And here you see two different kind of extrapolations to the continuum limit, just assuming a kind of dependence on lattice artifacts because we use a certain improved action. And you can see that in both cases within arrows, you get a coincidence of these constituents of this chiral multiplet. So this means yeah. Yeah. So basically here you see that this is in some units the lattice spacing, and you see as you approach the continuum limit, then you recover this multiplet structure.
Yeah, but so there is no way to the procedure which would be consistent with each state.
No, I mean this is unavoidable. So unless you have this kind of twisted formulations, you either end up with a non-local lattice formulation or you have to break supersymmetry. Yeah. No. Both are SU3 because this is order A lattice artifacts assumed, and this is order A squared lattice artifacts. We have added some improvements which reduce this order A lattice artifacts, but we are not completely sure whether we have removed all of them. Yeah.
Are there any sign problems?
Yes. So in principle, there is a mild sign problem here, which is also due to the fact that there are Wilson fermions used. So we can measure the sign of the Pfaffian, and we can just use a reweighting procedure. And in fact, for all of these results that are shown here, because we use improved lattice formulations, it turns out that this is a negligible factor, because it's it's so to say in a regime which is very close to the continuum. Okay. we have done further extensive studies of these theories. So we have determined the static potential as shown here, for example, for different, so this kappa means is just some inverse mass parameter. And so for different kind of masses, you can also measure the string tension of the theory and then extrapolate this to the supersymmetric limit. We have also done investigations of the running gauge coupling, which one example is shown here, where you can see that it indeed shows some QCD-like running. We have also confirmed this restoration of supersymmetry using supersymmetric ward identities, which is important because we use this chiral symmetry approach, and one has to really confirm that everything works consistently here. And we have also, there are also several determinations of the gluino condensate in supersymmetric Yang-Mills theory, which provide quite consistent results. There you have to be careful that some additional methods are needed, because with Wilson fermions you get some not only multiplicative but also additive randomization. So you have to use some methods to determine this, or you have to use domain wall or overlap fermions. But this has also been determined and measured. And we have studied the finite temperature transition of supersymmetric Yang-Mills theory. Well, this is a kind of energy scale, and this is the effective coupling. This is, yeah, I can tell you more details about the scheme, but yeah, so this is related to some gauge fixed vertices that are calculated, and then from the momentum dependence it is extracted. But we have also used other methods. Okay. Yeah, for any of these things, we can discuss also details if you want to.
What is confinement scale? Is X in what would you say confinement scale? Muscle.
We have determined also some lambda parameter that you can also define in this scheme. I can show you the details, but it's yeah, I just wanted to here summarize some of the results. I can later on show you the references and explain a little bit more about it. Okay. And the last thing I wanted to talk about, okay, is investigations of this compactified regime of supersymmetric Yang-Mills theory. So what you can see here is the expected phase diagram. As I said, the Witten index basically fixes to no phase transition here in the down to the semi-classical regime if you compactify the theory. And if you increase the mass, then at a certain point, there is some even calculable phase transition expected. And then this should connect to the Yang-Mills theory transition, of course, for infinite mass. This can be investigated on the lattice. And what we find is actually quite interesting, that in contrast to the thermal case, where you always have this deconfinement transition, the Polyakov loop rises at a certain point, that with periodic boundary conditions, if you lower the mass at a certain point, you see this kind of continuity. What is different from the expectation is that you get actually 3 different phases. So you get a confined, a deconfined, and a reconfined phase if you go to larger masses. So this means that on the lattice, we obtain basically such a phase diagram. At very low masses or high kappa, which then you end up with something where you don't see any phase transition, but at larger masses, you basically see some kind of intermediate phase here, which corresponds to an intermediate deconfined phase. So this is different from what is expected for the phase diagram, somewhat different. One can do further investigations, and one sees that basically in this regime where you go along this line here, then the theory stays basically in something that looks like a strong coupling phase. So the phase of the Polyakov line, this Polyakov line eigenvalues basically fluctuates only given like from the Haar measure. But then at even smaller radius, then you see something that looks, that is a continuous transition to something which looks like abelian confinement, so something that fixes the Polyakov loop to something that that stays in the, that fluctuates around some configuration that is confined. We have found the reason for the difference between the this continuum expectation and the and this lattice results in the lattice artifacts which are introduced by Wilson fermions. Basically, if you go along this line here, you reach at a certain point a scale where the radius, where the lattice spacing becomes not negligible compared to the radius, and therefore it sees what is called the doubling modes in this Wilson fermion formulation. So if you effectively see a larger number of fermions than you have, and therefore you can even use lattice perturbation theory to calculate then here this transition line in this regime here. So basically what you have to do is you have to go up to a certain scale here, and then you have to decrease the lattice spacing if you want to have a reliable regime if you go to smaller rate. But otherwise, basically this semi-classical regime can be reproduced quite nicely on the lattice.
You could take the smaller
Yes, yes. So basically what I would expect here is that this transition goes lower and that this line here continues and then becomes what is expected from. Yes, so basically, yeah, there's some kind of trivial scaling here. But I mean, you will never completely have something that at a certain point you will always reach the scale. Yes. Yes, but actually this phase there is not so different from it's still a confined phase, it's just a larger number of fermions that affect. So the latest thing that we have tried to study or started to study in collaboration also with Antonio Gonzalez Arroyo is to find some methods to get more insights in the semi-classical regime and maybe identify certain topological structures. And therefore, you have always the problem, of course, how to define topology on the lattice. And one usual method is that you use some cooling or gradient flow to smoothen the configuration. One additional method, which I found quite interesting, is that you also can use an adjoint zero mode of the adjoint Dirac operator, which gives you, if you have a background field that gauge field that is a solution of the equation of motion, gives you something that you can relate then to the topological density. So you can extract basically the information about FF dual just from this zero mode. There are some difficulties to formulate this on the lattice, but these techniques have been developed also already in previous situations there. And here's shown one example where you basically start with such a configuration, and then you can reliably extract these topological. This is basically the same configuration, but yeah, this is the topological charge distribution. Sorry? This is a snapshot. So you project the lattice, you take to one slice to two-dimensional plot, and then you plot this topological charge density. And then the information that is hidden behind this noise is basically shown here. So basically, yeah, I mean, this in both cases is of course 0, but these are artificially, this is an artificial construction. Still, it's not a simulation so far. So this, you put these instantones in, then you add some noise, and you see whether you can re-extract it. Yeah. Yeah. So yeah, I skip this further things here. And yeah, I just, yeah, the summary is that basically we have a large number of results already, and an open problem is still this, the lower end of the conformal window, which is also important for other theories here. And we are also have added scalar fields to the theories, but the problem there is to find some tuning which gives you, can give you supersymmetric QCD or n equals 2 supersymmetric anomalous theory. Yeah, thank you.
Maybe take a couple of questions, maybe just have like a 20 minutes. So, yeah, were they started from what? The confinement thing, the EPS here, is the grouping amount?
No, not so far, but yeah.
Yeah, we'll be discussing.
We are already discussing. Okay, but this is for the compactified theory, or is it also true for the? Okay.
Yeah, just wanted a couple of comments for technical one brand build. There is I think qualitative gravity rule or gravity rule.
Yeah, but yeah, but it's not that well established as for any four as I. But if you have some,
there is a finding background that qualitative.
Okay. Hey, we can discuss that.
But also, I think one tries to say two-dimensional and no Islamic or.
Yes. Well, there are some results for two-dimensional Young-Mills with adjoint fermions, but yeah. So there's only, I think there's only one lattice proceedings, and there are some results of n equals 1 supersymmetric Young-Mills theory reduced to 2 dimensions. Not that one.
Not that. SU and Young-Mills
With just
yeah, well, ideally one that.
Yeah, I mean, yeah.
I tried looking at it. That's what I'm.
Yeah, I mean, we have started to look at this as well, yeah, and the only reference that we found was some lattice proceedings, but not a complete analysis.
Is there any understand like one key component of the kernel can be relation temperature of the same.
So there are arguments by Witten, I think, which are string theory motivated, have been made that this should be the same. And then there are also some kind of effective theories developed by Uwe and Wieser and others, which describe this transition. So you have before the different vacua of the condensate, and afterwards the different vacua of the Polyakov loop, and then the domain walls. From the domain walls you get the domains, these new phases. So there is some kind of effective theory argument. I can show you these references.
No, but I haven't done
Is there any difference between SQL and the SQL theory?
Well, for supersymmetric Yamose theory, we investigated both, and at least the particle spectrum, and in some units of the string tension, actually the low state looks similar, but so for the conformal window, I think there are not really studies of larger NC. It's focused on SU2.
Now and about that important.
State of NF equals 1 is still unfolded.
Yes, I mean, with Andreas, I did quite a number of studies. Some of them
Okay, I think it's time to start. So our next speaker is Etsuko, and she will be talking about velocity of sound beyond the highest relativistic limit of that simulation of dense QCD. Just to mention that we
Okay. Okay. Yes. Okay. I should keep my time. So first of all, I'd like to thank the organizer for giving me opportunity and actually kind invitation to this workshop. So again, this is a lattice simulation talk, and subject is slightly changed. I'd like to talk about the kind of finite density QCD using a lattice simulation. And this is my main message. So we found the squared sound velocity normalized speed of light can be larger than 1/3. This is a value in the relativistic limit, free relativistic theory. Yeah, it is newly found by the lattice numerical simulation in the dense 2-color QCD. And this talk is based on the collaboration with Kei Ida-san in Kochi University and based on this paper. So, and let me start the why we studied 2-color QCD at the finite density region. So this is a general introduction. So this is a famous expected QCD diagram. So here we would like to consider, ideally, we would like to consider a finite density QCD. The Lagrangian is given by this equation. This is a standard QCD Lagrangian. And this is a number operator, and the associated coupling constant is a Quark chemical potential mu. And in this QCD phase diagram, vertical axis is the temperature, and the horizontal axis is the baryon density, but it is proportional to the mu Quark chemical potential. And as you know, lattice gauge theory is only known non-perturbative and gauge invariant regularization method. And as for the lattice Monte Carlo simulation, finite temperature at the 0 chemical potential region, this on the axis, lattice Monte Carlo simulation is available and it has been studied very well. However, in the other region, actually non-zero chemical potential region, Monte Carlo simulation failed because it suffered from the sign problem. I will explain this later. So, based on this situation, so we would like to consider that reduced model, so-called 2-color QCD. This is just a reduced model with a color degree of freedom in the real 3-color QCD. So we consider SU2 gauge theory with a fundamental fermions. And here in this slide, I'd like to explain, talk about the at least the 0 chemical potential region. This 2-color QCD has very similar property with the 3-color QCD. Actually, as you know, so at the 0 chemical potential region, standard QCD has these interesting non-perturbative or non-perturbative properties. And these qualitative property, 2-color QCD has the same property. And furthermore, here I'd like to say too much. Maybe as a quantitatively, for instance, equation of state as a function of the temperature shows a very similar, at least in the quantitative QCD, between the 2-color case, 2-color and the other color of color QCD. So actually, this is the plot of the trace anomaly normalized by the degree of freedom of the gluon. And so trace anomaly is given by the internal energy minus 3 pressure. And the horizontal axis is inverse of the temperature. And this is this shows a Quark gluon plasma phase, so high temperature phase. And there is several dotted line. This is given by the Marco Panero by lattice numerical simulation. He investigated the SU3, SU4, 5, 6, 8 pair gauge theory. And so you can see these data overlap each other. So I think Marco Panero would like to say there is already NC equals 3 is a large NC. And here, cyan and red data show the result of SU2. And you see there are some discrepancy between the other NC. Mainly it comes from the different 2 color QCD has a second order phase transition in the Quincy QCD, but the other NC has a first order phase transition. So around here is corresponded to the critical temperature. So here there are large discrepancy. However, naively speaking, qualitatively, 2 color QCD also has a qualitative same behavior, and quantitatively, at most, the difference is at most a factor 1.3 or so. So here I'd like to say, at least qualitatively and hopefully, yeah, I'd like to say quantitatively, 2 color QCD is a very similar property of the 3 color QCD, at least mu equals 0. And at the mu equal non-zero real QCD, we don't know anything. But in the case of 2 color QCD, sign problem is absent even at the non-zero chemical potential region. I will explain later. So we can perform the numerical simulation in the case of 2 color QCD, and we'd like to find the qualitatively and hopefully quantitative property of the real dense 3 color QCD from this simulation. This is our basic strategy. And actually, we have several papers from 2020. So today I'd like to briefly introduce our result, first and second paper. So here, first one, we investigate the QCD phase diagram in 2 color QCD using lattice simulation. And the second one is a collaboration with Yuya. So we gave some constraint on the 2 color QCD phase diagram in 2 color by using the Tofuft anomaly matching. And the main topic is based on this paper. So we investigate the velocity of sound using lattice simulation. Okay, so first of all, I'd like to talk about the what is sound velocity, and yeah, again, this is a QCD phase diagram. So in the case of 3 color QCD in finite temperature, actually we have a finite temperature phase transition and 150 MeV, and this is a plot of the obtained lattice result of the equation of state as a function of temperature. And you see here is a critical temperature, and you see pressure and thermal energy, thermal entropy and internal energy monotonically increase in the Quark in high temperature phase. And the corresponding sound velocity, actually sound velocity square is given by the del P over del E. And this quantity has a minimum around the TC. And in the QGP phase, it monotonically increases and finally approach to 1/3 in the ultra high temperature limit. This is a result of the hot QCD. And today we would like to consider what is happening in the finite density region. Actually, we would like to focus on the low temperature and high density region. And in the low density region, so this is a weakly interacting hadronic matter picture. So we can calculate some perturbative analysis. And in the ultra high density region, so in ultra high density region, quarks approach each other. So according to the asymptotic freedom, so quarks behaves like a free particle. So perturbative analysis is valid. So in the ultra high density region. So and it is expected plot of the sound velocity. So in low temperature, it grow up from 0. And in the ultra high density region, it is approached to the 1/3 again. So this is a value of the relativistic limit. But the problem is what is happening in the middle range of density. And actually, recently, it is a very important task to find the equation of state of the finite density QCD. Actually, recently, some experiment is ongoing. Actually, observation experiment is ongoing. For instance, neutron-neutron star merger or the gravitational wave, or nicer, it is another observation experiment of the neutron star. And actually, equation of state of the finite density QCD can encode the mass and radius relation of the neutron star. So this is a one-to-one corresponding plot. So if the equation of states, pressure and internal energy has some first order phase transition in the middle range density, then MR relation has a cusp in the middle range of density. So it is weird. And another scenario, if we extrapolate this low density and high density region using the linear function, then corresponding MR relation has a waving behavior. And another scenario, if we interpolate this region using some smooth function, then in some case, corresponding MR relation shows this shape. So this shape means the radius of neutron star is almost independent of the mass. And this is somehow consistent with the observed data of the neutron star. And in this case, the sound velocity, corresponding sound velocity, this quantity has a peak, and the peak height exceeds the 1/3. This is one possible scenario. Actually, several phenomenological prediction has been proposed by the observed data or effective model analysis. Actually, the sound velocity has a peak in the middle range of the density region. And I think first proposal given by the Masuda-san, Hatsuda-san, Takatsuka-san 10 years ago. And they consider, they actually propose the scenario, Quark-hadron crossover picture, which is consistent with observed neutron star MR relation. It suggests, this scenario suggests a square of sound velocity has a peak at the middle range of density region. And recently, Larry, McLaren, and Reddy also investigates the quark-ionic matter model. This is an effective model of the finite density QCD, and found again the sound velocity has a peak. And the most relevant paper for me, for us, is given by the Kojo-san and Suenaga-san last year. They gave some microscopic interpretation of the origin of the peak, so-called quark saturation. But the most important point is that this mechanism works for any number of color. Actually, in the Kojo-san, Suenaga-san's paper, they investigate the effective model of the two-color dense QCD, and they show that it has a peak in the middle range of density. So this is a strong motivation. We investigate the sound velocity using a lattice numerical simulation. And this is also a general slide, but once we would like to perform the numerical simulation at low temperature and high density QCD, we have at least two serious problems. The first one is a sign problem. This is a famous one. Once we add the quark chemical potential term, then Euclidean action takes a complex value. So standard Monte Carlo simulation cannot be available. And however, here we avoid the sign problem. Once we reduce the color degree of freedom to 2-color QCD, then quarks Quarks is a fundamental representation of SUN gauge theory. So in the case of SU2 gauge theory, quarks becomes a pseudo real representation. Then the sign problem is absent from the two-color QCD with even number of flavor. And the other serious problem is a so-called onset problem. It appears only in the low temperature and high density region. For instance, quark chemical potential is larger than half of pion mass or 1/3 of the nucleon mass. So beyond this threshold value, so pair creation because of this chemical potential emerge, then the calculation becomes unstable. And such instability comes from the actually phase transition from hadronic phase to the superfluid phase. And it is related with spontaneous symmetry breaking of the baryon symmetry. So to investigate such a spontaneous symmetry breaking of some symmetry, we usually add some explicit breaking term of the symmetry. For instance, Ising model case, so we add the external magnetic field, and in the case of chiral symmetry, we add the small mass, quark mass, and takes a massless limit. And in our case, explicit breaking term of the baryon symmetry can be given by this term, so-called diquark source term. Essentially, it is given by the psi bar minus psi. And the associated parameter is a J. So we perform the numerical, actually Monte Carlo simulation with this action, QCD action, and the number operator with quark chemical potential, and the diquark operator with parameter equal J. Then hybrid Monte Carlo exact algorithm, hybrid Monte Carlo simulation are doable in the whole temperature and density region. This is our strategy. And today I will show you several plots, but the J-Z extrapolation already taken in the old plot. Okay. So this is an introduction. And now I would like to show you our result. First of all, I'd like to show you the two-color QCD phase diagram. Actually, currently, there are several independent lattice groups, at least 3 independent lattice groups. So Simon Hans group and Russian group and our group. So different color denotes different collaboration result. And however, to my surprise, all data can be summarized by this plot, this picture. And first one surprising point is here. So actually, temperature is 100 MeV. Here we fix the scale TC. A chiral phase transition is 200 MeV. Then around the 100 MeV, superfluid phase emerge here. So before our study, actually this study, it was expected superfluid phase emerge only in the extremely low temperature. However, even 100 MeV, this paper has solid evidence of the emergence of the superfluidity. So this is one solid result of this work. And the second one is given by the Furusawa-san and Yuya. And according to the Tofu-Futa anomaly matching analysis, this is a purely analytical study. We obtained this constraint, confinement, deconfinement temperature is lower than the superfluid QG Coulomb plasma phase transition. So this dotted line, dotted curve is lower than this solid curve. So, and this lattice simulation is consistent with this prediction given by the Tofu-Futa anomaly matching. PEC. I will explain next slide. Yeah. Which one? QZP?
There's no one function.
Mhm.
Is the low temperature, low density separated from the phase by a phase?
This one. In actual lattice numerical simulation, there is no center symmetry. So this is, I think this is a crossover line. Okay. And let me explain our phase diagram more detail. So here, now I'd like to fix the temperature, roughly speaking, 80 MeV, and investigate the phase structure in this line. So, and first of all, the order parameter of superfluidity is a dicoke condensate, QQ. So in the case of 2-color QCD, QQ is a color singlet particle. And here is our actual data. So QQ dicoke condensate is 0 before the this critical value of mu. And beyond this critical value, so QQ has a non-zero value. So, and monotonically increase as a function of mu. And this magenta line shows a prediction given by the chiral perturbation theory. So the scaling behavior is consistent with this prediction of chiral perturbation theory. But anyway, this is this plot shows the emergence of the superfluidity. And Jeff's question. So in the superfluid phase, there are Bose-Einstein condensate phase and BCS phase. So, and this is a plot of the Quark number density. And actually, the vertical axis normalized by the tree level value. Actually, we can calculate the Quark number density by using the free Quark propagator. Then our data is in this region. It's consistent with unity. So in this region, free Quark picture is valid in the superfluid phase. So we identify this region as a BCS phase, and the other region we identify Beck phase. And this green dotted line is a guiding line of the where Beck BCS crossover occur. So this is our definition. So anyway, summary. This is a summary. So at this temperature, we have a hadronic phase, Beck phase, and BCS phase. So this is a summary. And now I'd like to show you our result of the equation of states. So to obtain the equation of states, we would like to know internal energy and pressure as a function of mu. And so we need at least two independent observable. And the first one is a trace anomaly. Trace anomaly is given by the beta function and the trace part of energy momentum tensor. And so the beta function, as for the beta function, we have 4 parameters in our Lagrangian. So first one is a gauge coupling constant. Here we denote the beta. And the second one is fermion mass. We denote it kappa because I'm lattice people. And the third one is mu, chemical potential. But the chemical potential is associated parameter of the number operator. And the number operator is non-renormalizable quantity, conserved quantity. So there is no renormalization for mu. And we also add the dicoke source term, associated parameter is J, but eventually we take the J0 limit, so this term can be 0. So essentially, we have to calculate the beta function of gauge coupling constant and the mass parameter, and essentially we have to measure the this one is actually F mu nu, and this one is essentially psi bar psi using the generated configuration. So this is a first step. And actually we have to obtain these beta function non-perturbatively non-perturbatively using the lattice simulation. And the third step is we obtain the pressure independently. So we can obtain the pressure by the numerical integration of the Quark number operator. I already showed our raw data in previous plot slide. So, and to be honest, so there are early works on the equation of state in the dense 2-color QCD by these people. However, they actually use the perturbative beta function here and here because non-perturbative determination of the beta function is very tough work. Actually, we need roughly 3 years to obtain these two values. But anyway, we have done, and yeah, that is a new point actually. Anyway, so we utilize these values and measure this quantity. Finally, we obtain the trace anomaly and pressure respectively. And here, I plotted the 3 data. So red one is first term of the trace anomaly. This one, coupling proportional to the beta function of the gauge coupling constant. And second term is described by the green data. And actually, green data come from the psi bar psi, and the psi bar psi actually is from the fermion loop. Then it gave a negative contribution to the trace anomaly. So in this plot, we flip the sign of the obtained quantity. So, and actually the sum of trace anomaly first term and second term is given by the red data minus green data. And in the hadronic phase, so red data is consistent with green one. So if we take the subtraction, then the total trace anomaly is consistent with 0 in hadronic phase. This is very reasonable because in hadronic phase is if we change the value of mu, the physical quantity does not change, so-called silver braid behavior phenomena. And in the Beck phase, red data is larger than green one. So red minus green data becomes positive in Beck phase. And in the BCS phase, red data is larger than green one. However, eventually green data is larger than red data. So trace anomaly in BCS phase is changed from the positive to negative. And it is natural because in the high density, fermion degree of freedom getting larger and larger, then fermion contribution also large. And blue data is a pressure. This is a monotonically increasing function, and it approaches to the this value, the value in the Stefan Boltzmann limit. Yeah, this is analytically obtained. And from the previous plot, finally, we can obtain the squared sound velocity, taking a ratio delta P over delta E. And again, sound velocity is consistent with 0 in hadronic phase, but it takes a non-zero value in the superfluid phase. And this blue curve is a prediction of the chiral perturbation theory given by the Son and Stefanov 2001. Actually, they investigate 3-color QCD with ice spin chemical potential, a little bit different modified model of the real finite density QCD. But this equation has a no-free parameter once we fix the value of critical chemical potential. So, and our data is consistent with this prediction, chiral perturbation theory, at least in the Beck phase. And the chiral perturbation theory says eventually sound velocity goes to speed of light. So I think people believe at some point this chiral perturbation theory will fail. Actually, our lattice data far from this prediction in the high density region. However, here I'd like to stress our data of sound velocity exceeds this orange line. This is 1/3 the relativistic limit value. So this is our result. And let me explain what is new. So as I explained it, so far we know the finite temperature phase transition, and around the in the case of finite temperature QCD, so sound velocity has a minimum around TC and monotonically increase in the high temperature region. So the value of sound velocity always lower than 1/3. However, in at least a 2-color 2-flavor QCD at the finite density region, so sound velocity can be larger than 1/3. And it is previously unknown from any lattice calculation for the QCD-like theory. And actually, this is there is a famous bound, so-called holography bound or conformal limit given by Alex more than 10 years ago. And actually, I have to say, this paper is correct because this paper investigates finite temperature gauge theory, and they gave a bound. So sound velocity is smaller than 1/3. But they give a conjecture in the last sentence of the abstract. And so they gave a conjecture. It may be valid for the broad class of 4-dimensional theories. But here I have to say it is incorrect. So yeah, this is, but many people believe that this holography bound so far. Yes. Okay, thank you. Yes, yeah, actually finite temperature and finite density is a quite different behavior. Yeah. Okay, and I think you would like to know what is happen further high density region. And actually, we have upper bound of chemical potential in the lattice numerical simulation. It comes from the mu in lattice unit should be smaller than 1. Otherwise, our numerical simulation data suffer from large discretization error. So this is the upper bound in our simulation. And to study the more high density region, so we have to perform the lighter mass simulation to make small, to obtain the small pion mass, or final lattice simulation to keep this constraint. But both directions need expensive calculation, so we cannot do immediately. And so according to the perturbative QCD prediction, so people believe it is valid in the ultra high density region. So according to perturbative QCD analysis, sound velocity approach to 1/3 from below, then one minimum scenario is sound velocity is 0 in hadronic phase, and it increases and actually excess the relativistic bound, and it decreases once, and again it increases and approaches to 1/3 in the ultra high density region. This is one possible simplest scenario. However, there is another expectation in the high density region. So once people he considered the power correction due to the Diocoke gap in the superfluid phase, then a square sound velocity can be larger than 1/3 and approach to 1/3 from above. And Fujimoto-san and Fukushima-san, Kenji, also gave another prediction using the hard thermal loop resummation. And in this case, again, speed of sound approach to 1/3 from above. So still it is an open question how square sound velocity approach to 1/3 from below or from above. So this is one open question. And so, okay, this is a summary slide. Actually, we found the sound velocity exceeds the relativistic limit in finite density QCD-like theory. And one of the most important question is what is the mechanism of such a excess or peak structure of sound velocity? And according to the several effective model analysis, there are several scenarios. Quark saturation given by the Kojo-san and Suenaga-san, and strong coupling with trace anomaly given by Larry and Kenji. And there are several scenarios. And now we investigate the actually hadronic force in the try to formulate the how to investigate the hadronic force in the superfluid phase. So at least zero chemical potential region, we have a Lucia method or HAL-QCD method to investigate the hadronic force. And so we try to extend the HAL-QCD method into the finite density region. Actually, I have to say that the large sound velocity indicate the higher pressure as a function of energy. So, and the higher pressure might be induced repulsive force between the hadron. So this is a naive expectation. And here we would like to confirm that such a repulsive force between hadrons is emerged in the superfluid phase. But to be honest, in the case of two-color QCD, it is special because in the case of two-color QCD, all hadron, actually meson and baryon is a boson. So, and the bosonic theory has a repulsive force. Otherwise, vacuum collapse, decay, become unstable. So we believe that there is some repulsive force between the hadron in two-color QCD. So, but the most important question is such a mechanism is independent of the color degree of freedom. And this is a final plot. This is not my result. Actually, Bastian here gave a similar result. Actually, they working on the three-color QCD with isospin chemical potential, which is also another toy model of the real three-color QCD. And this case, sign problem is absent. And they show that even in this model, the sound velocity exceeds the 1/3 conformal bound by lattice numerical simulation. It is very promising and encourage us. So, okay, that is all. Thank you very much.
Questions? Very interesting stuff. So, in some of your thoughts, I saw that your lattice result began to disagree with parallel perturbation theory. It's just fairly early, right? Around
Good. Good, very good point. And actually, I skipped the detail of the phase diagram. You can see that this space. So this is corresponding to the here and the region. And actually, there is a thermal excitation of the quarks, actually hadrons. So this yeah. But this is, we'd like to say zero temperature, but it is low temperature, but not exactly zero. So yeah, yes, there is small thermal excitation. Yeah. Kenji's result. I'm sorry, I don't understand this result. I have some understanding this scenario, but yeah, so sorry. Please ask Kenji.
Thanks a lot for all this stuff.
Yeah.
One of the wild ideas, I guess people had in the old days is that some density, there will be a lattice of area, another like a crystal. And then I guess the sound waves will be crystal and break. I think one other such explanation is out of
Crystal.
like a neutron crystal.
Actually, I don't, maybe I don't know the,
Yeah.
yeah. Mhm.
Yeah, so I mean, what you're suggesting is that you have a large flexibility, right?
Uh-huh. Uh-huh. Okay.
Yeah, I think it exists somewhere at intermediate density, like you see this peak as intermediate.
Mhm.
But then at really high density it will turn into Quark matter, but maybe.
Mhm. Yeah. Yeah.
Functional randomization. That's from the other side.
Mhm. Yeah. Sorry. Sorry, I don't know. But yeah, I remember you told me in the Lattice conference, but sorry, I didn't check. I definitely will.
Right.
Mm.
You're saying that when it's going up, we still have some trace of pad bonds there. And then when it goes down, somehow we've associated it with quarks, the simple quark.
Yeah, actually, there are still unclear point because I didn't explain, but yeah, in the QCD phase diagram in Tukara, it is expected there are two BCS phase, so-called BCS phase with confinement. So I mean, this is a hadronic superfluid phase. And in the case of 3 color QCD, we believe that there is a quarkionic quark superconductor phase. But in the case of 2 color QCD, actually the diquark is a singlet. So it is expected the confinement remain in the ultra high density region. So once we observe this local quantity, so-called the quark number density, so we the value is consistent with a free quark picture. However, in the macroscopic scale, it is expected the confinement properties remained in the 2 color QCD. So I think it is another different point from the real 3 color QCD. Yeah, but it is still unknown. This blue region goes to the goes down or not. Yeah, this is an open question.
There are no more questions. Let's speak now.
Yeah.
Don't forget that 3:45